Seismic surveys for wind farm projects are shot at ultra-high resolution in order to better image the shallow sediments, which determine where you can install these wind turbines. Oftentimes, due to the sheer size of these datasets as well as the complexity, it can be quite difficult to analyze and interpret them quickly. Pre-trained machine learning models are oftentimes ineffective on these types of surveys, especially since they were trained at the ENP scale, which is much different from the ultra-high resolution scale. However, we can leverage interactive deep learning to guide the neural network to identify and characterize those shallow geologic features as well as shallow hazards so that we can install offshore wind turbines at scale. Now, in the previous episode, we talked about a recent shift within the AI community, going from a model-centric approach to one that is more data-centric. With interactive deep learning, we take a data-centric approach. And what's critical here is that the geoscientists interacts with the neural network in a live bidirectional feedback loop where they can now guide the neural network through a process of label optimization. We can use VDS's open source adaptive wavelet compression to actually reduce the size of these datasets, make them easier to work with, but at the same time, we're able to have minimal loss in both the amplitude and frequency information. A multi-class ENet with a focal dice loss function was used to train and characterize a simple stratigraphic framework. This was trained for about 50 epochs, and we labeled less than 1% of the dataset. From this, we could then create a 3D mask, where we could now better characterize some of the incised valleys, but also only focus on a particular interval of interest. The 3D masking significantly improved incised channel valley predictions, while also mitigating some of the mispredictions for both seismic noise as well as seismic multiples. Here, that neural network was trained for about 47 iterations. The interactive methodology allowed us to actually refine our labels throughout the training process live in this bidirectional feedback loop. And that was critical so that one, we could get better results, but also achieve a better prediction in a shorter amount of time. The 3D masks were actually critical because they helped us only focus on a specific zone of interest while also filtering out noise and seismic multiples. Using an interactive deep learning approach like interactive AI, we were able to successfully characterize the shallow geologic intervals as well as the complex incised valleys in about 20 hours, so under a day. And what's critical is that these outputs can then be used directly into the geomodeling process so that now we can identify these shallow hazard zones, but then also optimally install these offshore wind turbines at scale.